situation where it matters. Let's take cocaine. And if I react this with H3O plus, what am I going to get? Now, I'm not going to suffer rearrangements here. This one's going to be one where it's fairly unambiguous. What will the product be here? Okay. In using acid as a catalyst, we add water to the double bond. Hydrogen will go here. OH will go here. That's what we call a Markovnikov addition. Remember this from General Chemistry 1? And Markovnikov's rule stated the carbon with the most hydrogens gets the hydrogen in this kind of reaction. We know that it really arises as a consequence of the stability of the carbocation. The thing that forms first, or the thing that adds first, is an H+. The catalyst hydrogen adds here, putting the carbocation here, giving us a secondary carbocation, rather than one that would arise where hydrogen adds here and puts the carbocation here. You understand what I'm talking about? Okay. And so we get a Markovnikov alcohol. Even though we don't suffer rearrangements here, this is not a great way to make this, because there's a competing reaction, the formation of ether, and there's a competing reaction, or it's an equilibrium reaction. In other words, I can take an alcohol and put it in acid, and it will dehydrate to form the alkene. Okay, and so even though this is a quick and dirty way to make an alcohol, it's not a way to make alcohols in good yields, in high purity. But that's what we're talking about here. The oxymercuration, demercuration reaction is what? Remember?
It's another Markovnikov alcohol.
Yeah, I treat the alkene with mercury 2 acetate. Remember that?
Mm-hmm.
Okay, and it's a two-step reaction. What's the second step?
The NaBH4.
Yes, sodium borohydride. And so I treat it with mercury acetate, then sodium borohydride in the second step, and I get the Markovnikov alcohol in high yields. Okay, even though it involves working with a mercury compound, as long as we're working with adequate precautions, it's a good way to get high yield Markovnikov alcohols. The anti-Markovnikov alcohol would have the OH here and the hydrogen here. If I desire that, I can use the hydroboration oxidation reaction, where I use borane, BH3, followed by what?
Peroxide.
Yeah, basic sodium hydroxide, or hydrogen peroxide. Sodium hydroxide and hydrogen peroxide in a two-step reaction. That gives me high yields of the anti-Markovnikov alcohol. So, quick and easy, low yields, high yields of a Markovnikov, high yields of an anti-Markovnikov. So we've got three good strategies here, depending on what our needs are. One is cheap and easy. All we need is dilute acid, but we don't tend to get high yields. If we distill the reaction or the products out, we might be able to get decent yields here. The other two give us high yields.
Can you show us the two competing reactions really quick? You said at one it'll form an ethane and the other one's a...
If I have, let's do the alcohol. Let's start with the alcohol. This is the reverse reaction.
Oh, okay.
Is one of the competing reactions. If I have hydrogen right here, what will that alcohol do?
Oh, so it comes on.
It'll pick up the hydrogen and give me this guy. Looks like that.
Okay.
This will come off as water, and we put carbocation here, and then hydrogen can come off of here and give me the alkene. So this is just the reverse reaction of what we were just talking about.
Okay.
Okay. I can also, under certain circumstances, create an ether here. Okay, and we'll talk about that in more detail when we get to chapter 14.
Okay.
All right. Now, we also, there's a good chance in talking about alkenes, we talked about making diols. Vicinal diols are 1,2 diols where the alcohol groups are side by side. And there's a couple of ways of doing it. If I want the syn hydroxylation, which means what?
Like the anti kind of?
It's actually a cis product.
I don't know this.
Okay, in other words, the alcohol groups are added on the same side of the double bond. So we call a syn or cis product as a consequence. We use either osmium tetroxide followed by hydrogen peroxide or cold dilute potassium permanganate. We don't want to use real aggressive permanganate here because it actually oxidizes the double bonds to aldehydes, ketones, and carboxylic acids. So we need to work with a tamer version of the permanganate. Both of these will produce, and if I do this with a cyclic alkene, for example, let's say we're talking about cyclopentene, permanganate, I get the syn hydroxylation. In other words, I get a cis diol, 1,2 diol. And the osmium tetroxide hydrogen peroxide combo will give us that as well.
No, if it's not cyclic, it doesn't matter, right? I mean,
What's that?
if it's not cyclic, it'll just spin.
If it's not cyclic, you're right. However, we can get different enantiomers and meso compounds that are possible if the alcohols produce chiral carbons. And then we have to actually do a lot more detailed inspection of the carbons themselves. Okay, so there's some stereochemical consequences. If I want an anti, what do I use?
Carboxylic
I use a proxy acid, metachloroperoxybenzoic acid. Remember that, way back?
acid.
Okay. And what that does is it produces an epoxide, like that. And that's treated with acid to give us the anti-glycol. We're dredging up chemistry from a while back. That gives us this guy. Anti-addition to give us a trans-glycol. Does that make sense? Two different approaches to make a 1,2 or vicinal diol. And these are reactions, and if you don't remember them, you probably ought to just go back and briefly review right out of the alkene chapter. Now, we're going to get into some exciting stuff. At least I think it's exciting. We're going to talk about organometallic reagents. This is new for everybody. These are Grignard reactions. And there's besides the Grignard reagent, alkyl lithium compounds fit into the same category. And I shouldn't call them all Grignard reagents. But it looks like this. Carbon, when it's covalently bonded to either magnesium or lithium, if we look at our table of electronegativities, we discover that carbon is more electronegative than magnesium or lithium. That will mean that the bond will be polar with carbon carrying a partial negative charge. And even though that there's a covalent bond there, the carbon will act as though it's a carbanion. Okay? And it'll be a very strong nucleophile and a very strong base, both. And so when we produce these Grignard reagents that contain a carbon-magnesium covalent bond, the resulting product, the Grignard product, will act as a powerful nucleophile and a powerful base. And some reactions that we're going to look at. All right? Now, this reaction is, I think you're doing a Grignard reaction in the laboratory.
Yeah, we are.
I'm excited for you. Make sure that you keep things scrupulously dry. In other words, one thing that's recommended is when you do the reaction, keep the glassware in an oven for 10 or 15 minutes, higher than the boiling temperature of water, just to get the surface very dry. And we, by luck, it seems like every time we do this reaction, it's a rainy day outside, so the humidity is up. You can actually see the difference in the yields as a consequence of high humidity. So do everything in your power to keep the reaction dry, and the yields will go up. What happens is we take a halide, treat it with magnesium and make a Grignard reagent, and then it can be reacted with a carbonyl compound to make alcohols. That's the bottom line. Let's look at chemistry. Here's an alkyl halide, can be chlorine, bromine, or iodine. We don't use fluorides here, it doesn't work. We react it with magnesium metal. It's done in ethyl diethyl ether, or sometimes it's called ether or ethyl ether. And here's my organo-magnesium halide. The magnesium literally inserts itself between the carbon and the halogen. So we've got two unusual covalent bonds here. This is called the Grignard reagent. It's pronounced Grignard, not Grignard. It looks like it ought to be Grignard, but this is correct, what we're pronouncing here. This behaves like it's a carbanion, which is a strong nucleophile. This will react then with anything that nucleophiles react with. And it will react with things that bases react with, because this thing is a powerful base and a nucleophile. And it's not really that hard to do. You just take your halide, put a little bit of polished magnesium pieces, warm it gently in ether, and usually the reaction is spontaneous. It takes off on its own and goes. And you'll usually see some sort of a color change. The reaction tends to get darker as this forms. So you'll be able to see that it's happening. So far, so good? Okay. Now, here's an example. Here's bromobenzene reacted with magnesium in diethyl ether, and the ether is essential. Okay, you can't run this in just any solid. And water is the enemy, alcohols are the enemy, a number of other things that can react with the Grignard reagent and neutralize it need to be scrupulously avoided. And here is our Grignard reagent. Here's another one where we're doing a secondary halide with Grignard reagent. We can do this with alkyl halides, alkeno halides. What do you think I mean by alkeno halides?
With the double bond in it.
Yeah, where the chlorine is on, or bromine, or iodine is on a double bond with carbon. They work too. And aromatic halides. So this thing is very, very general. Right? These are our Grignard reagents. Organolithium compounds, done pretty much the same way. I take a halide, react it with lithium metal, and I create the alkyl lithium. These things are not quite as reactive, not quite as aggressive as the Grignard reagent. Okay, and as a consequence, we can use these with solvents other than ether. There's a wider variety. The ether happens to stabilize the Grignard reagent. And that's why we use it there. But for the alkyl lithium, we don't need it. It just turns out that most folks have a lot better access to magnesium metal than they do lithium metal. Now, here's